Okay, so let's talk about our next reaction. This reaction is acid-catalyzed hydration. Again, this is another alkene addition reaction that we're going to be looking at, all right? And again, our reactant, our starting material is an alkene. We're going to be starting an alkene. And first thing I want to do is sort of talk about the reagents. See, what we see here is I've listed H2SO4, H3O plus as a reagent. And basically there's kind of a long list of what reagent we can add. So essentially, because this is acid catalyzed, right, we need a dilute acid, okay? The specific acids we use are not HCl or HBr. We've already seen that reaction. So generally, the two acids we use are H2SO4 or H3PO4, if I'm going to be specific about what acid. Now, these are dilute, so sometimes I might write H2SO4 and in the parentheses write DIL for dilute, or H3PO4 dilute. We could also write this as H2SO4, comma, water, right? Or H3PO4, again, comma or a slash water. So these are generally ways I can describe we have an acid-catalyzed reaction. Now here I'm specifying the specific acid we use. We can also kind of just talk about a generic acid. So you might see me write something like H3O plus, right? I could also write H plus, comma, water. And again, instead of using a comma, sometimes we can just use a slash, H plus and H2O. So if you remember from our kind of exercise talking about acids and bases, it turns out that these acids, H2SO4, H3PO4, are all really strong acids. So when you have them in the presence of water, you're actually going to be forming the hydronium ion H3O+. So that's why I might generally write H3O+ or H+ in water, all right? And you see, if we have H3O+, here's the structure of H3O+, right? You can kind of think of this as being in equilibrium with an H+ and a water molecule. Oops. Let's go back. Not a 3, a 2, and a water molecule. So it turns out that H3O+ is generally the species that we have in solution. So in solution, you're really going to have this H3O+ species. You're not going to have a free proton in solution. It's going to be attached to basically a water molecule. But you'll see when I'm writing mechanisms, it's easier to just use the H+, right? So I want us to understand that this is the actual species we have in solution, but generally when I'm writing mechanisms, I'm just going to write the H+, all right? So the first aspect of this is understanding there's a lot of different ways I can write the reagent, and they basically all mean the same thing. All right, H2SO4 dilute, H3PO4 dilute, or in the presence of water, or kind of just writing our generic acids, H3O+ or H+. All right, so let's go back to kind of looking at our reaction, right, knowing that we're going to list our reagents in different ways. What we see in this reaction as an alkene addition reaction, we're going to break the pi bond, right? So we're going to break the pi bond of the double bond. We're going to be adding our H and our OH across that bond, and we're going to be following Markovnikov's rule, meaning the H will go to the side where there's more H's, and the OH will go to the more substituted side, all right? When we learn a new reaction, there's really two skills we have to know. First, we have to know the reaction, right? So again, if we look here at these two sp2 carbons, right, following Markovnikov's rule, we add the OH to the more substituted carbon, right? Which means that we had one hydrogen here, right? And we've now added our other hydrogen there, okay? So we have to know the reaction, right? And generally speaking, I'm going to give you, if there's three pieces of information, we have our reactant, we have our reagent, and we have our product. I'm generally going to be giving you two out of the three. So I might give you our reactant and our reagent, and then you have to draw the product, right? That's typically what we do. Or I might give you our reactant and our product, and then you have to draw the reagent to complete the transformation, to complete the reaction. So that's kind of the first skill set we have to, is just know the reaction, all right? The second thing we have to know is the mechanism, right? So sometimes I'll ask you to draw out the mechanism of the reaction. We have to understand how that works, right? So I want to do that now. I want to show you the mechanism on how we do it. And it's going to be very similar to our HX addition mechanism, all right? So let's clean this up a bit. The mechanism for both of these examples is going to be the same. I'm going to do the mechanism for the bottom example here, all right? So when we have H2SO4 or H3O plus, right, we can just kind of think about this of having an H plus and water. And this makes our mechanism a little easier to do. So in our first step in our mechanism, we are going to protonate the alkene. Right? I draw our equilibrium here. I write the letter P. So when I grade this, you don't have to write the letter P. Like if you look at a textbook or other resources, they don't do that. But I like to add these letters to just remind you on, help you remember the mechanisms. So when we protonate this, we're going to follow Markovnikov's rule, right? We have two sp2 carbons here and here. So we're going to follow Markovnikov's rule and add the hydrogen to the sp2 carbon that has more hydrogens. Right? So hydrogen in black. We've now added this hydrogen in orange. And we now have this sp2 carbon here that only had, or was an sp2 carbon. Still is, but we have this carbon that only forms 3 bonds, right? So we have to recognize that by drawing a plus. That carbon in green is a carbocation. So this is a species that has a carbon that's missing a bond. It does not have a full octet. So we know that this species is a very good electrophile. So now we have to look at what is a good nucleophile. Okay, and again, anything that has a lone pair can act as a good nucleophile, and that's the role water is going to play here. So water is going to be our nucleophile. So one of these lone pairs is going to attack. It's going to form a new bond from the O to this carbocation. So here's my attack step. Now it's important to note, here's my new bond in orange. All we've done is convert this lone pair into that bond. Everything else on the O stays the same. So the O had 2 lone pairs. Now it only has 1, because this lone pair became the bond, and that O is still connected to 2 hydrogens. So if we count our valence electrons here, oxygen has 3 bonds. That's 3 valence electrons, plus a lone pair. That gets us 2 more electrons for a total of 5. But oxygen wants to have 6, right? So it's missing 1 electron on how many it wants, right? 6 minus 5 gives us 1. So it's important that we remember that this oxygen therefore has a positive charge, right? That oxygen has a positive charge. So if you look at our final product, right, the product we're making in these are alcohols. The O's are only connected to one H. So there's one step left, right? We have to get rid of an H and a plus. We have to get rid of a proton. We're going to deprotonate. So I'm now going to take another equivalent of water, H2O with two lone pairs, and I'm going to use this lone pair to steal a hydrogen and allow the two electrons from the bond become a lone pair on the O. Right, so this O here is now going to have two lone pairs and two bonds, so that O will be neutral. Right, we want our final product to be neutral. So again, what this means is this lone pair is being connected to that H. We're forming a new bond there, and this lone pair is becoming, or that bond is becoming a lone pair on the O. That gets us to our final product, an alcohol, right? Plus, we're reforming our acid, H3O+. All right, so that's why this reaction is catalyzed, because we're reforming our H3O+, right? Now, if I ask you to draw the mechanism, I don't really need you to include the plus H3O, or the H3O+, the hydronium ion. We're just really focused on the carbon atoms, right? So to draw the mechanism, we want to draw the arrow, show our equilibrium, draw the intermediate, draw our arrow again attacking, draw the intermediate, and then show the arrow attacking again to form our final product. So it's okay to not include this even though we're forming it, because we just want to focus on carbons since this is organic chemistry. All right, so this is the reaction of acid-catalyzed hydration. We are forming an alcohol, right? So we see that we know the reaction and we know the mechanism.